Thanks. So we go on with the complexity theoretic questions. And the next speaker is Sevag Gharibian from Paderborn.
Good. So thanks very much for the introduction. So this is joint, hold on, where's my laser pointer? Okay, I can use this thing, I suppose, no? Good. So this is joint work with my students, Yorgos Karaiskos, who is in the back. Put up your hand, Yorgos. Okay. That's Dorian Rudolph, sitting next to him. Put up your hand. So they did a lot of work on this paper. So if you have questions, bug them. Johannes is also the third student on this paper who also had a nice contribution to it. He just had a baby, so he's nowhere near us right now, rightfully so. Jens is also on this paper, and I am the last author. By the way, most people call me Sev, so you can do the same. Okay, good. You're allowed to do that. Oh, and feel free to interrupt me at any time in the talk. I mean, not to call my name, but if you have any questions, okay, it's fine if I don't finish the talk. The more you understand, the happier I am. Okay, so as you can tell, the theme of this work is going to be how hard is it to verify a classical shadow. So let me motivate this question with a simple, concrete example. So here is a shadow of a fish, right? And you know from your everyday lives that, if you look at a shadow, it's very difficult to figure out the properties of the fish, right? Let's say its weight, its dimensions. There's all sorts of factors that come into play. The angle at which the light is, hitting this fish, the angle at which you're standing to the fish. There's disturbances in the water, so on and so forth, right? So it's a really complicated thing, and it's not until you really step back and look at the big picture that you realize that actually, this isn't a fish at all, right? It's actually a duck. Okay, and so this brings us to the motivating question of this work, right? How hard is it to check that a shadow represents what you actually think it represents? Okay, so let me start by giving you a background on classical shadows. I'm sure how many people know what classical shadows are to some extent at least, or you've probably heard of it. Okay, good. So less than half, so it's good I put these slides in. Let's take it slow, let's take it easy. We're talking about ducks, so let's continue. So let's imagine you are a duck enthusiast, and you are interested in a set of certain properties of ducks, like their weight, their size, and so forth. Let's just call these pi, and there's m of these properties. So how do classical shadows work? Well, what you do is you first hire your favorite wildlife photographer, also known as a physicist, and you ask them to repeat the following for n days. Every day, your physicist goes into the wild, also known as the lab, and finds a copy of your duck, which will, lovingly name Ro. And what the wildlife photographer / physicist does, it takes a picture of the duck, like we'll call that a snapshot, SI. And of course, ducks are fragile creatures, like the snapshot scares them, so they run away or they fly away. That's a collapse. This experiment most certainly does not work with Canadian geese. They are assholes. They will kick your ass, so this only works with ducks. I know, ask me how I know. Okay, so, and at the end of this experiment, at the end days, the photographer hands you the stack of n photos, snapshots, and this set is what we'll call the shadow. I'll give you a more formal definition later. Okay, and your job is what? Like, you didn't go into the wild, and you're interested in these properties. So the question is, given the stack of photos, which are like 2D images, right? And classical post-processing, you want to predict the values of all these properties for your duck. And so the key question, or the magic of this shadows frameworks, is that how many pictures you need to take of the duck to figure out all these properties. And the surprising thing, which Aronson already showed in 2018, is that you can get by with a lot less photos than you would expect. So exponentially fewer than the number of properties you're interested in. The caveat here of this original work was that it was not time efficient, but this didn't take long. Shortly thereafter, Huang, Kueng, and Preskill, which I'll henceforth refer to as HKP in this talk, gave this very nice, I think celebrated, very simple and elegant framework for efficiently doing classical shadows. Okay, so I'm basically going to replace the word duck with like math symbols now. Okay, so the framework is essentially the same. You have a set of properties you're interested in. It's still pi. I'm going to have to add this ensemble of unitaries because this is going to dictate the bases in which we measure, like how we take the pictures. And we repeat this following experiment n times, right? You produce your duck or your n-qubit state row in the lab, and then you take a picture of it every day. Okay, so in this framework, you pick a random unitary from your ensemble U, you just measure your state in that basis, and you measure in the standard basis. I mean, you do the rotation, then you measure in the standard basis, and this just gives you a string, the snapshot. Okay? And so you compile all these snapshots together, and you do some post-processing, and this framework will provably allow you to predict all of these properties to within some additive error epsilon. Okay? And let me be clear, like the framework right now is not fully specified, right? I haven't told you what this ensemble U is. Depends on what properties you're interested in. But generally speaking, they give a bound on the sample complexity, like how many photos you have to take. And what I want you to take away from this here is that, again, you have this exponential savings, right? You have to take you only require log m pictures if you want to predict m properties. Okay? This ugly thing depends now on your choice of P and U. I'll say more about that in a second. Any questions on this slide? Okay. Now, in the HKP paper, there are two instantiations of this framework, which we'll talk about. So here's the first one. The first one is if you're only interested in predicting k local observables of your state. Okay? And here, the random measurements you need to do, it turns out, are just single qubit Clifford measurements. Okay? And when you do this, it turns out the sample complexity you need is basically, scales like 4 to the locality of the observables you want to predict. That's this k up here. And so as long as you're talking about, say, constant local observables, this is an efficient scheme. Okay, and certainly these measurements are very easy to conduct in the lab, at least in theory. Okay. So this is what I'll henceforth refer to as the local Clifford scheme. The other scheme they have, and which we'll talk about, is the global Clifford scheme. And here, this works for arbitrary properties, though we'll pay for it. The random measurements here are still, random Cliffords, but now they're global. Okay, so Jonas touched on this as well yesterday, right? So this is they had an improvement to this scheme. And so in here, again, you have this log m sample complexity, but we'll come to this again later. The runtime depends on the Frobenius norm of these observables. Okay, so it's only efficient when the Frobenius norm is at most polynomial. Good. So these are the two schemes I will talk about regarding HKP. Any questions here? Okay. Good. So now we come to the central question of this work, which is, if I give you a set of these snapshots, right, this set of pictures, how hard is it to verify if what you're looking at is actually a duck, right? Like these pictures represent some quantum state. Okay. And before we begin, I'm a computer scientist, a theoretical computer scientist, which means I like to be rigorous. And so we need to first formally define what it means to even have a classical shadow. Okay, so I'm going to do that first. You can probably guess where this picture came from, ChatGPT. Unlike Anthony, who's using it to do actual work, this is what I'm doing with my time. I ran out of my free queries very quickly. Yeah. Yeah, I'm going to define that, yes, in a second, yes, absolutely. Yeah. But the simplest version to state this problem of consistency is this, but you're absolutely right, yeah, that's going to be important. Good, so here's my formal definition, yeah? So we're going to be very general on purpose. So a shadow for us is going to be basically a 3-tuple of 3 elements, okay? So number 1, you have the shadow itself, which is basically this multi-set of snapshots you took, okay? And these are just like poly n-bit strings. And it's important that this is a multi-set, okay? So you can have multiple copies of the same string because you get the same measurement result, right? The second thing are the observables you want to predict the values of, okay? And here we're going to allow the observables in principle, depending on the setting, to scale to be even exponentially many observables, okay? And I'll come to that later. Of course, if we have exponentially many observables, we have to assume that they're uniformly generated, okay? Which means that there's some classical Turing machine. You give me the index of your favorite observable, and it will produce the description of that observable efficiently, okay? And finally, the last thing you need is some sort of recovery algorithm, right, that makes sense of the data. And so there's an efficient classical algorithm, which given the stack of pictures and your favorite observable produces some estimate to that observable, okay? And notice how in this definition, I'm not claiming anything about how good that estimate is, right? This is just a fully general definition of what counts as a valid shadow for me. Yeah?
So why do you limit the observables if it's exponential to 2 to the n and not 4 to the n?
Oh, just to keep life simple. Yeah. Okay. There's no particular reason. It should actually be, sorry, actually right, it should be 4 to the end. That's actually a typo. Yeah, because we will consider the case of the poly string. So good, thank you. That's a very good question. Typo to fix before archive deadline, Yorgos. Okay, thank you. Good, so where does the accuracy come in? It's gonna come in here for this, this is the formal problem we'll study, classical shadow validity. And the input here is just a shadow. And in the yes case, you're promised that there is a global state rho, so that the output of this recovery algorithm, given the snapshots, is close to what it should be. And in the no case, there's going to be some index so that you will deviate from that expectation value. Okay, and these are inverse polynomially separated. So this is the problem we're going to study for the rest of this talk. If you're unhappy with it, make sure you ask me the question now. Okay, good. So now I can state our results. So our results we can categorize into 3 categories or sets. The first one will be for polynomially many observables. Okay, so let's focus on that setting first. So the first thing we prove is hardness results. And we show that this verifying a classical shadow basically is quantum NP hard, okay? Even for these super simple protocols, like the local Clifford HKP, where you're doing these 1-qubit measurements, you get these strings, the inversion map is like super simple, so this is still QMA hard. And essentially, it's even hard if your observables are more or less on like a line. They just overlap on like nearest neighbor. It's a little bit more complicated than that, hence I have this, this set of words here, but it's essentially on a line. Okay, so this is a hardness result. And there's recently been a high-dimensional generalization of GKP, and so we can extend this technique to also work for this high-dimensional generalization of Mao, Yi, and Zhu. But I won't say more about that in this work. Okay. I'm sorry? I've been hanging around like the photonics people too much. This is my problem. I swear this has happened multiple times. I caught them all, but not this one clearly. Thank you. Okay, good. So the next thing we do is we're still in the polynomially many setting, right? So this hardness result was for this local Clifford scheme. If we go to that global Clifford scheme, which is the second instantiation I showed you of HKP, then we can show that if you assume like the standard like dequantization assumptions of query and sampling access to each of these observables, then as long as these observables are bounded in Frobenius norm, we can essentially dequantize, or we can efficiently solve this shadow verification problem. Okay, I call it dequantization simply because we need this sampling access. Think of it that way. Okay, and so this may or may not seem restrictive, but this is exactly the regime in which the original HKP scheme here was efficient to begin with. So this basically means that you can dequantize the entire scheme as far as we care. Okay. And a similar result goes for the higher dimensional version of Mao, Yi, and Zhu. This is all I'm going to say about polynomially many observables. Any questions so far? Yeah?
What's the meaning of sampling access to the
Okay, so the observables are big. These are not local. They don't have a succinct description. And so you assume that because it's a matrix, you can essentially sample a row index by the probability of sampling the index is relative to the weight of that row relative to the weight of all the rows combined.
Okay, so this is basically like the Tang model.
Yeah, absolutely, absolutely. This is like the old school randomized linear algebra. Yeah, absolutely. So we use like a Fries, Kanan, and Van-Pala behind the scenes. This is, yeah, absolutely. Any other questions? Okay. Good. So now we move to this setting of exponentially many observables, where there's this very astute question of, don't you mean 4 to the n instead of 2 to the n? And this question, this may sound kind of ridiculous, right, at first glance. But since you have this like exponential savings in the number of photos you need to take of your duck, it's meaningful to ask this question. And in fact, there was this nice paper, I think it was technically released in 24, triply efficient shadow tomography by King, Gossett, Kotari, and Babush. And there they gave a shadow protocol for the set of essentially all n-bit Pauli strings. Okay, let me clarify here that their protocol has polynomial sample complexity, but the time complexity is still exponential. But for us, that's irrelevant because for us, the shadow is already given an input as input, so I'm not paying for the time complexity of generating it. Okay, we're just given the shadow. What's the difficulty of verifying it? The other nice thing their algorithm has is this rapid recovery property, which is that if you only care about constant precision additive error, you can actually recover the observable expectations in polytime, even though there are exponentially many of them. Okay, so for each one, obviously in polytime. Okay, so the next thing we show is that this problem for exponentially many observables and in constant error, so even when you just want weak error, like in this rapid recovery, this is complete for something harder than QMA. Okay, and of course you expect this, right? Because how in the world is the QMA verifier going to check exponentially many observables? That's ridiculous, right? So you have to go higher, and where we go higher is basically this class here. It's a quantum generalization of sigma 2, which is the second level of the polynomial hierarchy. And if you don't know what that is, that's fine. Basically, here's a very brief definition to give you a flavor. This part is just like QMA. There exists a quantum proof psi, and then now you have a for all quantifier over all classical proofs y. Okay, so this is the new part, and the verifier in the S case will accept these two proofs together. Okay, and so what I like about this result, there's pros and cons, right? I wanted to put the cons first, but Yorgos insisted that the pros should come first. So in the submission to QIP, the cons came first, and now in this slides, the pros come first. So the pro is that this is the first natural complete problem for a quantum analog of sigma 2. There are a couple of works on this area, but I was really annoyed because we didn't have a complete problem yet, a good one. The con is that unlike for HKP, we're not able to show the results for this nice set of observables yet. The observables we have in our reduction are, artificial. So this is a nice open question. Any questions here? Okay. So the last set of results is about variants of this problem. So for example, you might ask, is there a consistent state with the shadow which has a certain structural form, say it's product, right? And then we can show analogous results in the sense that if you care about polynomially many observables, the complexity is now QMA2 complete instead of QMA. And QMA2 is just QMA, but now the proof is promised to have like some cut in the middle where it's in tensor product. And if you have exponentially many observables, then you're talking about yet another level up in this quantum polynomial hierarchy, basically. Okay. And finally, maybe you wanted something different. Maybe you believe your source of shadows in the cloud, that they're giving you a valid shadow, but now you have a bunch of them lying on your desk and you don't remember which ones they are, which states they correspond to. So can you check that they're all consistent with the same state? Or are they just copies of each other? And again, we get similar results here. It's QMA complete for polynomially observables, and that quantum polynomial hierarchy complete for exponentially many observables. Okay, that's all I'm going to say about results. Any questions? Okay, by the way, Robert, I did not thank you at the beginning. You're doing a great job. This is a great workshop. No, it's a lot of work to put this together, so thank you, honestly. Like this is, we appreciate it. Okay, good. Proof sketch for so I'm only going to show you that first theorem that it's QMA hard in the interest of time to do the local Clifford HKP, okay? So here's the theorem, let me just remind you. We show that it's QMA hard to verify shadows of this basic local Clifford form. And where's the starting point? Like if you've ever thought about complexity theory, you probably know this consistency of local density matrices problem of Yikai Liu, right? And so this is a very well-known problem. Here you've got these k local density matrices, they act on k qubits at a time. And the question is also a consistency problem, is there a global n qubit state rho which is consistent with all of these little baby rho i's? Okay, did anybody think of this problem when I first stated the shadow validity problem? Yeah, good, okay. So the idea is that, look, this is like suspiciously like this other problem, right? So if this problem is QMA hard, certainly our problem must be QMA hard too, right? And indeed, like our general definition of CSV is like so general that you get QMA hardness for free because classical, like consistency of local density matrices is a special case of our very general definition of CSV. So that's not the point of this paper, right? The point of this paper is that classical shadows look nothing like local density matrices, right? So we wanted to cover the shadows we see in practice, and in particular these HKP shadows. And the difficulty is that unlike these local reduced states, if I want to take a bunch of these and map them to shadows, these guys are highly non-local objects. They act on all n qubits at a time. And so if I want to do a reduction from consistency to HKP, I basically have to deal with this like age-old nasty problem of taking local data and stitching it together to get a global state. And anybody who's worked on this problem knows that they hate it, okay? It's a difficult problem. And not only that, we have to do it, of course, while simulating the structure of the HKP protocol, right? Because it's got to be for that protocol, the hardness. Okay. So this is the challenge. Now, in order to show you how the proof goes, I need to tell you a little bit more about how exactly how this protocol works, okay, what the snapshots look like. So let's just go back to, this is previously what I had. So you've got k-local observables in this HKP local Clifford protocol. The measurements you're making on each copy of your state are independent single qubit Clifford measurements, which basically means that given row, pick Pauli x, y, or z at random and measure in its eigenbasis. Okay, so you get one of 6 possible states as the outcome. And we'll just let psi I be the result obtained for qubit I. Okay, so from this, you want to construct your snapshot, which is like the picture of the duck. And so formally, the way you do this in their protocol is you just construct this classical, you write it down. This is a non-positive operator, but that's fine. And you do this on qubit j, because on qubit j, oh, sorry, this is also a typo. This should be an I. You saw result psi I. Okay, so you take n of these together, what you got on each qubit, and you stitch them together in tensor product. This is the classical shadow. And you'll notice that this is a n-local operator. It is not k-local like a reduced density matrix. Okay, and finally you take these all together, and this gives you your full classical shadow. Okay, so what is our goal now? Our goal is we wanted to do a reduction from local consistency into classical shadows, right? So the input to our problem is going to be these k-local states. Maybe they act on like 3 qubits at a time, like on qubits 1, 2, and 5. And I want to map it to these now n-local snapshots of this form. They look like this. So here's one snapshot, for example. Here's another. And I have to do this in such a way that 2 properties hold. So number 1, in order to maintain the QMA hardness of the problem, it must be the case that my input density operators for the local consistency problem were themselves globally consistent. If and only if this list of snapshots I produce in my reduction, the frequency of any one picture occurring is consistent with measuring some global row according to random local Cliffords, as done in this protocol. Okay, this is the main key thing. And then formally, the other thing that's really nice, and that we will use this property explicitly in their protocols, if you take the expectation over the snapshots Si, you in expectation get exactly the target state. So we were also going to, of course, require this property and enforce it. Okay, any questions about this? Because the next slide is just going to go through sketch the proof, and it's basically going to go through this thing. And so if you have a question.
So I have this question here.
Yeah, sure.
For the second one. So
yeah.
Here you mean that you take a particular reconstruction protocol or any reconstruction protocol?
We are over here.
Yeah, well, what do you mean by this expectation value?
Oh, so good. So what I mean is that we're going to produce shadows of this form so that it basically mimics what's happening in the HKP protocol.
Sure.
And one of the key properties of the HKP setup, not just for this protocol, I think it holds for any of their protocols in that framework though, is that if you take the expectation of the shadows, by definition, you can see very quickly that it gives you exactly the target state.
Yeah, those operators, yeah, sure. But,
yeah.
But there are other duals. This is like over complete basis. So there are other ways of doing it.
We won't talk about that. We're just literally focusing on this exact protocol. Okay. Because I really like that protocol.
Okay.
Okay. Good. Any other questions? Okay. Good. So I'll cram it onto one slide. I'm just going to give you a high-level idea. Okay. So we want to do reduction from consistency, but remember I said that basically what we have are these really annoying, well, let me not draw it yet, but we have these local reduced states, and they overlap on some qubits, and stitching them together into these non-local shadows is going to be a total pain in the ass. So the first observation is that if we actually work on the 1D consistency problem, okay, so this just means that our observables just act locally, like on a chain basically. So think of it as, here's here's row 1, row 2. Sorry, not observables, but the reduced states. It looks like this, row 2, row 3, and so forth. Okay, now these are going to have to be QDITs, because 1D problems to be hard typically require QDITs. Okay, so if we start in 1D, the idea is going to be that in some sense this will be easier for us to then stitch together these nearest neighbor local states. Okay, so to do this, we first show QMA hardness under many one reductions. Let me be clear, Yukai had a result under Turing reductions for this already 2 decades ago, but nowadays we have the many one reduction techniques, which are listed here. So we went through the motions and combined this locally simulatable codes of Broadbent and Grillo, and the 1D QMA hardness constructions for local Hamiltonian due to Hallgren et al. And so this is our starting point. So even in 1D, the consistency problem is hard as long as I have 8-dimensional systems. Okay, step 1. So the next thing is that HKP does not work on qubits, it works on qubits. So I'm going to do the obvious thing, which is that I'll take each of these 8-dimensional qubits and I'll rewrite it as a triple of qubits. Okay, so each triple is now Ti, and so here I'm going to replace this. Actually, I should use a different color with a triple of qubits, and this will be another triple of qubits, and so forth. Okay, so this is maybe Ti. This is now Ti plus 1. Okay, and so what we can do now is that these are still local objects, right? So this is still just 3 qubits, this is 3 qubits. So I can iterate all possible local shadows according to the HKP protocol on just these 6 qubits, right? There's only 6 possible stabilizer states on each qubit, so this is easy. It's constant size. So I'm going to do that over here. And now the next step is that we want to stitch these together with, in principle, a global object. So it turns out we can write down a linear program to compute still at the level of local snapshots. I'm not doing anything global yet. Okay, but onto each of the local snapshots, onto these baby sets, how much probability in terms of measurements should I put on each of these local snapshots so that the local probabilities, interesting, are consistent with a global HKP shadow? Oh, clean toilet, that should really not be up there. I did it last week. Damn thing. Okay.
Although it's due today, though.
Well, that means it's typically overdue. That means I ignored it. No, but I did clean it last week. Because I didn't clean it the week before, I know. I maintain a meticulous bathroom. Okay. Okay, so we want the local probabilities to be consistent with a global HKP shadow, of course, if and only if the original 1D consistency instance we started with was also consistent, okay? So we can write an LP to do that, and here we're really going to use that nice property that the expectation of measurements should give you exactly this state. This is important, okay? This is a linear program. The problem with this is that the linear program returns, of course, real numbers. I have no control over this in general. But in the snapshots we have, right, the only control I have to control probabilities is I have to repeat a picture an integer number of times, and that should correspond to the frequency of measurement outcomes. And so I don't want real numbers, I want integers. So I'm going to do something completely counterintuitive. Nobody in their right minds does this. I'm going to go from an LP back to an integer program. Okay? So I'll round it, and if you can solve this, then you'll get integer weights on the local snapshots. Okay, and the problem with this now is that, well, integer programs suck, right? They're hard to solve in general. But here again, for the second time, we'll really use the fact that we started with a 1D instance. Because in 1D, it turns out you can solve this integer program efficiently. Okay? And that's via dynamic programming. There's a history of 1D problems being solved efficiently via dynamic programming. Good, so all of this is just to kind of locally put probabilities on these little baby shadows in this local space here, like this, each of them looking like a tensor product of stabilizer states on a single qubit. The last thing is to just stitch them all together into a big N local shadow. And to do this, we know that they're in principle consistent in the sense of the integer program tells us this, but we still have to stitch them together. And so here we have to use a perfect matching and appropriate permutations and just to collect them in a certain way so that when we add them all up, we'll get something that's locally consistent with the reduced states we started with. Okay, this is the end of my technical component. Questions?
So for the
solving the integer program. So why do you need the polytime algorithm in the end if you want to?
Oh, because it's a reduction. That's good. Because the reduction, I have to be able to output. Like my goal is to, I have these guys as input, and now I need to output like those strings S1 to Sn, so I need to compute those efficiently. Yeah, that's a good question, yeah. Okay, so let me just quickly summarize. We formally defined classical shadows, and we talked about their verification. For the local Clifford protocol of HKP, it's QMA hard. For the global Clifford protocol, we can dequantize it, and we can even say something about exponentially many observables. But I think this is a nice open question of, can we get something for the King, Gossett, Kotai, Babush protocol for this observable set when you have exponentially many observables? Okay, according to my watch, I'm out of time, so I will give you one more shadow picture, which I thought was too morbid to put at the beginning. I didn't want to crush your soul right away, but there was also the option of starting with this. And this is the solution, okay? Anyway, thank you for your attention.
Thanks a lot for this great and entertaining talk, Sev. So maybe we have time for 2-ish questions. Yes.
So my interpretation, oh yeah, sure.
Yeah.
So my interpretation of your results is that like if someone samples from a non-quantum state and pretends that they are giving you a classical shadow, then it's like QMA hard to...
In the worst case, yeah.
In the worst case.
In the worst case.
Then it's QMA hard to distinguish whether there's which of the two things they're doing.
Yes.
But have you thought about the hardness of actually spoofing the classical shadow? Like how would one actually do this?
No. That's a good question. No, I haven't, yeah. But I think that's a good next step. Yeah.
Thanks. Any further questions? Okay, so let me ask an inappropriate question about that. Okay, so you showed this distinction between the local APK protocol,
Yeah, sure.
and the global one, or
Yeah.
and but do you think you just said the word is in the worst case. Do you think in typical situations it will be hard, or what is your feeling? Or I know that this is not exactly what you want to look into.
No, this is. I mean, it's a fair question because in practice, I always like to say, as a complexity theorist, I'm not the one doing the real work, right? The people in the lab actually solving these problems, they have to do it numerically, right? So I don't have a good answer, I think. We do certainly have a history of NP-hard problems. Certain ones, like SAT, for example, are very well solvable in practice.
Yes,
I don't have a good feeling for consistency problems at all, to be honest with you. So
yes.
I'm sorry, I don't think I can give you a good answer there.
Yeah. That's why I was saying it's not completely proper.
I think it's worth studying, yeah.
Yes. So if nobody is doing it, so thanks again for this great talk, Sev. And the last talk before